Hi guys on YouTube land. So we had been talking on Monday about redox reactions. And we said that these were reactions which were driven by an exchange of electrons, which meant there was a chemical giving electrons away. And we said that was the chemical that was being oxidized. There was also a chemical which was receiving electrons. And we said that was a chemical which was being reduced. And so that redox reaction showed those electrons moving from one chemical to another. Now, we often get clues that the reaction is a redox because when we look at the chemicals, they might begin with an electrical charge, and then that electrical charge finishes by the end of the reaction. Or maybe the chemical starts without electrical charge, but finishes with electrical charge. That's a sure sign that electrons are being passed around between the chemicals. So we'll look at these simple ones. Be aware that there are sometimes more complex examples where the charge is kind of camouflage, so to speak, because amongst the products you might get something like silver chloride, which is an ionic compound, and of course is made up of silver ions and chloride ions. So sometimes the electrical charge is kind of disguised in a chemical formula. But for the most part, we'll avoid those examples just to keep things simple. It is, after all, a 100 level course. Okay, so here's the latest one. We had finished on Monday on campus with this previous example. I think that's right. Alexei can confirm that. Was that the last one we did, Alexei? The lithium reacting with the iron? Yes, she says. Okay. Let's see. So let's look at the next. Get on the page. I have to use my mouse for this bit. Let's look at the next one and break it down. So we're looking at the full reaction here, but we're going to break it down into those two half reactions, looking at the progress of one chemical at a time. So let's start with the silver. And so it starts as Ag1+. By the end of the reaction, it finishes as precipitated silver metal. So let's track where those electrons are coming from and going to. Oh, we've got another volunteer. Haley's trying to get in. And so as we look at this one, of course, we can track the subatomic particles using the periodic table. So as we look for the atomic number of silver, let's see, oh, way too big. Silver in our transition block, of course, there she is there. Element number 47, which means that we have 47 protons in an atom of silver or an ion. Now that charge tells us that the number of electrons at this point for each of these ions, remember there's 3 of them, and we are just looking at the atomic particle count for one atom at a time. Number of electrons, to make the math work, must be just 46. Plus 47 minus 46, it gives us the +1 charge. Now by the end of the reaction, we've got silver metal, still 47 positively charged protons, but to come up with that 0 charge, as we have 0 charge here, which is why it's left blank, that only happens if there's also 47 electrons. So let's look at the electron count. We started with 46, we went up to 47. We are missing an electron at the start for each of these silver ions. One more electron would give us a 47 as we finish with. So we are adding those electrons back into the half equation. But remember, that's just for one of those 3 atoms of silver. So 3 of them collectively would be missing 3 times the electrons. So 3 electrons goes into our half equation. It doesn't have the electrons yet, but they've been put into the shells of each silver ion by the end. It's gaining electrons. And when we're gaining electrons, it's reduction. The silver is being reduced. Now, if we look at the chromium for its part, again, let's build its own. Let me use a different color just to be fancy-smancy. Let's use a nice orange. So the chromium chemically changing into chromic ions, Free+. That's a charge of chromium with a Free+ charge, chromic. And again, we can check for the subatomic particles. Let's see, chromium, is that element number 23? I have to check. Chromium, actually one off, 24 for chromium. As you see through all this scroll here, the chromium is atomic number 24 because it's the 24th element. So each of those atoms has 24 protons, but to have neutrality at the beginning, 0 charge, that would only happen if there was 24 electrons. Again, the simple math shows us the way. For the chromium ion, the chromic at the end, to be chromium, it's still going to be 24 protons. And here comes Hannah to join us. Still 24 positively charged protons. But with that charge of 3+, the only way that happens is when there's just 21 electrons. 24 minus 21 gives us the 3+. So this chromium started with 24 electrons, but finished with just 21. So we've got 3 electrons missing on the right-hand side of the equation. So let's add those electrons back in. The electrons are here because they're no longer part of the atom. So that's electrons which have been lost. When electrons are lost, that's the oxidation step. Oxidation is the loss of electrons. And when we're looking at the 2 halves of this full reaction here between silver and chromium, the total electrons lost is always equal to the total electrons gained because it's the same 3 electrons. Electrons given up by the chromium, and those electrons are picked up by the silver, each of those 3 silver ions. And so the chromium, which is being oxidized, is supplying the electrons to make the reduction happen. And so we sometimes call the chemical oxidized a reducing agent, like a Hollywood agent who makes all the deals for an actor. The reducing agent is supplying the electrons to make that reduction happen. On the reverse side of the coin, the chemical being reduced, the silver, it's taking the electrons away from the chromium. And so it's almost as if it's making the oxidation happen by taking those electrons. And so any chemical that's reduced can also be referred to as an oxidizing agent. Work out if the chemical is reduced by gaining electrons or oxidized by giving electrons away. And then just simply remember it's the agent for the other process. So anything oxidized is a reducing agent. Anything reduced is an oxidizing agent. It's always the agent for the other process. So there's our example number 3 with silver and chromium. I've got a few more to go over. Probably a fairly short lecture for today. Let's see, I need to clear this. Let's look at the next one. This one completed for us this time. So reaction of copper with silver this time. You see the copper turning into copper ions, the cupric, 2+ charge. The silver ions turning into silver metal again. There is a pecking order for the metals and elements in terms of how good or bad they are at giving or receiving electrons. And if we split them up into their own separate equations, let's do the copper first. So copper turning into those copper 2+ ions. Again, we can check the periodic table for the atomic number. You'd always have a periodic table in an exam. 29 for copper, so 29 positively charged protons. And if there's no electrical charge at the beginning for the copper, it must be because it's neutral. It has an equal number of electrons. That's the only way for the atom to be electrically neutral. So 29 electrons, but with that 2+ charge at the end, that means that there has to be just 27 electrons when the reaction is finished. So it went from 29 down to 27. We're missing 2 electrons on the right-hand side of the equation. And we can put those electrons back in. They are no longer part of the atom, which is why we show them as a separate chemical. And so the copper having given away electrons, the copper metal specifically, that's the chemical which is oxidized, or it's the oxidation step. With the silver, that means it has to be the chemical reduced. And we can show that with our subatomic particles. Again, 47 protons, as we said for silver. But with a charge of +1, that means that we only have 46 electrons. The final silver metal, which is precipitated out as a solid, remember that S in parentheses tells us we have a solid. That means that we've got 0 charge when there's nothing written there. If it's part of its own unique formula and there's nothing written for charge, it must be electrically neutral. You only get away with not showing charge if it's part of a chemical compound. So 47 electrons when we finish. We only started with 46. And so there's an electron missing for each of those silver ions. And that needs to be added back into the equation. But remember, that's for each of the silver ions. There's a second one, 2 of them altogether. So twice the number of electrons missing. So 2 electrons in total. And that makes sense because when we look at our 2 half steps, the copper being oxidized is giving away 2 electrons, and the silver being reduced is receiving 2 electrons. Total electrons lost and gained should always match up. Like a cash transaction on eBay. If you buy something for $50, your account will be -50, and the person selling that item for $50 will be plus $50 in their account. So we can track the money as we can track the electrons on the 2 sides of the equation. Any questions about that one? We're doing okay? And of course, with oxidized and reduced chemicals, Our copper, while being oxidized, it's the supplier of electrons for the reduction. So we can also think of it as a reducing agent. The silver being reduced, it's taking these electrons from the copper. So we can think about it as an oxidizing agent. Okay. Couple more left before we can put this chapter to the side. There's a Chem Talk video for this coming soon. And definitely some question of the day videos as well. So next one, we're talking about the reaction between sodium and tin. We can again break it down into their own, excuse me, there's just a tiny, tiny little flea buzzing around in front of me because of the brightness of my screen. I keep just about getting it and then it disappears again. So, sorry, sodium, if we look at the sodium half first across the equation, start with sodium atoms, finish with sodium ions. Again, looking at the periodic table for the atomic number of sodium, element number 11. So 11 positively charged protons in each sodium atom or ion. We have no charge at the beginning. That means that we must have 11 electrons to cancel with those 11 protons. But by the end, in that 1 plus charge, we only have 10 electrons in each of those ions, hence the plus 1 charge. So we're missing an electron for each of the sodium ions by the end. And so 2 of them collectively would be missing 2 electrons. Electrons given away at the end. At this point, they're no longer part of the atom, which is why they're shown as a separate entity. So the sodium has lost those electrons and has been oxidized. If we look at the tin, these tin ions turning into solid tin metal precipitated out of the reaction, presumably, with the atomic number for tin being 50. Where are we? There we are. 50 protons for tin. If it has a charge of plus 2, it means we've only got 48 negatively charged electrons. By the end, with the charge gone, there must be 50 electrons matching the 50 protons. And so we're missing 2 electrons at the beginning. We can add them back into the equation, either before or after the chemical symbol for the tin, the stannous. Doesn't matter which way around, it's just a list. So this and this and this going into the reaction, or if it's the products, this and this and this and this coming out of the reaction. Order doesn't matter as long as it's on the correct side of the arrow itself, because that's our pivoting point. Again, the total electrons being gained in reduction matches the total electrons being given away in the oxidation, as we looked at a second ago. So total electrons gained and lost will always match up. Here's another one, the potassium reacting with silver hydrogen carbonate. Again, a slightly trickier one because we've got one of these polyatomic ions we mentioned. Hydrogen carbonate as well as the silver. So what is the underlying charge based on the ionic formula? Split into the 2 half equations and then work out oxidized and reduced species. So we'll take a break for 5 minutes while people think about that, and then we'll come back and finish off our last few examples for the hour. Hello, Internet, and we are back. So let's take a look at this one. Let's handle the relatively, well, I guess they're both slightly tricky because of the polyatomic ion. So let's start with the potassium. So potassium starts simple enough on its own. and then as it chemically changes, it becomes part of this potassium hydrogen carbonate. Now, of course, hydrogen carbonate we should recognize because it's one of our polyatomic ions from chapter 3. And it has a charge and formula of HCO3 minus 1. That's just straight out of the notes. We should be familiar with all of our polyatomic ions. So for all charge to come to 0, as we expect with any ionic compound, that potassium in the compound must have a counter charge of +1. So the potassium atom changing to a potassium ion. And we can check for our subatomic particles, of course, looking at the periodic table. So potassium, element number 19, 19 protons in every potassium atom. So if there's no electrical charge at the beginning of all this, we only have 0 charge because there's 19 electrons as well. By the end of the reaction, we still have those 19 protons. Can't change the number of protons without changing the identity. But that +1 charge is telling us that there's only 18 electrons at this point. Started with 19, finished with 18. We are missing an electron on the right-hand side of the equation. And so we'll add that back in. This is an electron which is lost because by the end it's no longer part of the atom. And so when electrons are lost, that's of course our oxidation step. On the other hand, with the silver, part of silver hydrogen carbonate, just like we did with the potassium, it's an ionic compound which collectively must cancel to 0, so that -1 charge of the hydrogen carbonate is countered by the +1 charge of the silver. Because it cancels to 0, we don't normally see those individual charges shown in the chemical formula. So for the silver, we've got the Ag+, which turns into Ag, or silver metal. Again, looking at the atomic number, did we say 47 for silver? I'm just going to check because I'm paranoid. Yep, 47 for silver. 47 positively charged protons. And with that +1 charge, the math tells us that there must be just 46 electrons. Meanwhile, the final silver metal with 47 protons, no charge, and therefore 47 electrons. So we're missing an electron at the beginning, and we can add that back into a half equation. And so at the end of the reaction, that electron has gone, it's disappeared because it's gone into the atom's shell, it's picked it up. And that of course is the reduction step. Chemicals which gain electrons, pick them up, are being reduced. So the potassium being oxidized, it supplies the electrons for the reduction to happen. So we can call it, or refer to it as a reducing agent. And the silver being reduced, it's taking the electron from the potassium. We can refer to it as a oxidizing agent. It's always the agent for the other process. Excuse me. Any questions about that one? Total electrons lost have to match the total electrons gained. Let's see what we've got left. Can't be much, I'd imagine. One good example of redox reactions at work in medicine, of course, is a pacemaker. Inside the pacemaker, there's lithium and iodine, and they exchange electrons to produce lithium iodide. We break it down into the individual components, lithium and iodine. Lithium changing into lithium ions, that's the charge when it's part of lithium iodide. That iodine changing into iodide ions, that's the charge when it's part of lithium. +1, -1, and charge cancels out. And so we see that the lithium is giving away 2 electrons, well, the iodine is picking up those 2 electrons and reduced. Again, we can check the atomic numbers to make sure this is correct. Let's see, where's my pen? Here it is. So lithium, of course, third element in the table. It has 3 positively charged protons, and without any charge, there must be 3 negatively charged electrons. For that ion, it's produced 3 protons, but now only 2 electrons. And so 3 to 2, we're missing an electron on the right. And then for that second lithium ion, we're missing a second electron. For the iodine, no charge. And so those 127 positively charged protons in each iodine atom must be matched with 127 negatively charged electrons. By the end of it, we still have 127. Actually, I'm getting that all wrong, aren't I? What's the atomic number for? Because I'm thinking of mass, because I've been doing spectroscopy with the other class. I beg your pardon. Iodine. What is the atomic number for iodine? Ah, there we go. 127 mass. 53. Tut tut, Dr. E. You almost made a big boo-boo until you caught yourself there. Okay. I do apologize for that. Getting excited there, apparently. 53, right. So 53 positively charged protons for each atom. And with neutrality, it must be 53 electrons. By the finish, still 53 protons, but that -1 charge for each of the ions tells us we have 54 electrons. So we're missing an electron for each atom of iodine. Collectively, we're missing 2. So the total electrons lost matches the total electrons gained. And as those electrons get transferred from one chemical to another, they get passed around the heart muscle while that chemical reaction is ongoing. So those electrons primarily turn up in 3 areas of the heart. Apologies for the picture here. That's massive. Nobody has a heart that big.
Unless they're super kind.
I guess. And slightly wrong position, of course. But basically, the electrons travel across the surface of the heart, which is what is sometimes referred to as the epicardium. Also within the heart muscle itself, the tissue, the myocardium, then inside the heart cavity itself, the endocardium as well. And so the pace of that electrical current produced is something that the heart muscle instinctively takes up, hence the term pacemaker. So we can speed up or slow down the electrical current, the rate of those electrons being fired off, and it controls the patient's heart rate. Incredibly ingenious machine. That looks like it's it. Sometimes I have one more example in, but it doesn't look like today, or what we now do. I guess I decided we just had enough. Okay, so that finishes the chapter. Yeah, like just know everything. Read the book, read the text. Okay, so that
Here's
puts
another highlight couple.
chapter 5 to the sword. So remember, there are no classes on Friday. I might, if I get the time on Friday, I might dig up an old exam and do a video on one of the old chapter 5 exams. That will give people something to look at. But otherwise, chapter 5 is finished for section 1, and we'll move on to chapter 6 next week. That is the biggie, guys. Chapter 6 is the biggie. Do not spend the first week studying chapter 5 because your chapter 5 exam is coming up. Keep abreast with the chapter 6 material as you're studying for chapter 5. Okay, any questions before we call it a day and head for lunch? Okay, remember, homework is up. Polling questions are up for chapter 5, and they close on Tuesday and Wednesday next week. The lab assignment for next week is climate change experiment number 6. And our magic word, of course, for this week is Avengers. So if I ask you what the magic word is, it is Avengers. Don't tell anybody else. Let them work that out for themselves. Okay. Bye, guys. I'll talk to everybody soon. Oh, one question before we finish off. What is that? Indeed. Okay. I'll talk to everybody soon.